All right, let's get this thing going. Oh. All right, last class we discussed chi-squared tests. And it's a different distribution. It's not a normal distribution. It's skewed. And it helps us determine if two sets of data, well, there's three types of chi-squared tests. Last one, we did the chi-squared goodness of fit test. That's for goodness of fit. And what that does is it compares some categorical data to a claimed distribution. Right? If the company claims it's a certain distribution, we will see if that claim is correct. All right, now today we're going to do two different other chi-squared tests. The first one is, I think it's pronounced homogeneity, for sure, homogeneity. And basically what we're going to do is we're going to take two samples, and they have to be categorical, meaning fit in a category. We have male and female. We're going to take a sample of male. We're going to take a sample of female. And the males might guess whatever the survey is. They might guess yes, no, or maybe. And the females might guess yes, no, or maybe. And we're going to compare to see if there is a difference in the two samples, or if there's a big difference. Now, obviously, there's a discrepancy between the number of males that answered yes and the number of females that answered yes. But is it a big discrepancy? Is it a big deal? Is that discrepancy enough to say, whoa, hold on here, these two samples are different? All right, so that's what the chi-square test for homogeneity. We're testing to see if they're all the same. We're testing to see if male and female are the same for whatever this questionnaire is. All right, so go ahead and read through this for me. All right, let's go with Chloe.
Would you vote for a female president? For a class project, Johnny and Sally wanted to know if the gender of an interviewer could affect the responses to a survey question. The subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president, by a female interviewer. The other half of the males were asked the same question by a male interviewer. The table shows the results.
All right, okay. So actually, it's two samples of men being asked. These men are being asked by a man interviewer, and these men are being asked by a female interviewer. So the question next is, how many samples do we have, and what population are they from? So we have two samples, as you can tell. So two samples. To do a test for homogeneity, you do need two samples because you're pairing two samples. All right, so it's two samples. 50, that's a 5 and a 0. 50 males asked by females. Asked by female. And 50 males asked by males. Now, in a perfect world, there wouldn't be a big discrepancy between the results of these. All right, but you know, even in a perfect world, you're not going to get exactly the same. There's going to be variability between your samples, and so really the question is, how much is our variability? Is our variability a big deal or not? So how many variables are we examining? We are examining one variable. It's the response to this question. Yes, no, maybe. This is the one that's varying as far as there's two samples, but within both samples there's one variable. One variable, the response to the question. All right. For this particular test, we are going to do a significance test. We need some hypotheses. Remember, these oppose each other, and the null is always kind of the boring one, equals 0, or there's no difference, or the claim is true, or in this case, there is no difference. All right, so we would say there is no difference in the distribution of blah, 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 blah. Okay? So for us, it's there's no difference in the distribution of the responses for the men asked by male interviewer versus the men asked by female interviewer of the question, would you vote for a female president? Okay, so that whole thing, that's the whole context. And I get it from the question itself. All right. And then the alternative is there is a difference. So the difference is no. There is a difference in the distribution. Now, you can stop there. Actually, well, yeah. So opposing hypotheses, always, they're kind of negating each other. Opposites. All right, now we need to come up with the expected value. Because if you remember in the chi-square test, what you do is you compare the observed with what you would expect to get. All right, so under our null hypothesis, we expect there to be no difference in the male and female. So in this case. So what we can do there, now because these are nicely split 50-50, and there's a total of 69 that voted yes, if there was no difference, we would expect this to just be split 50-50. 34.5 and 34.5. That's what we would expect to have. All right. So the real question is, how far off are our observed values from what we would expect to get under perfect equal distribution? Now, sometimes you're not going to have exactly 50-50. And so there's a formula for this. And it goes like this. The probability, so now we're going to do some probability again. The probability of being asked by a male and saying yes would be the following. Be the same as the probability of being asked by a male and saying yes, because they would be independent events. And so there were 50 males out of 100. There were 69 yeses out of 100. And so the probability of being in this box here is, well, we can figure that out. I calculated that out already. That's 50 times 69 out of 100. Hold on. Just wait. Hold on. Let me save that for the end. This ends up being, I didn't calculate that yet. Shoot. Interesting. 60 times 69. Divided by 100, divided by 100. All right, 0.34. Boy, that's what that ends up being. So what this tells you is that 34.5% of your population should go in this box. Because they're not always going to be the same. This one works out really nicely. And so then you take that 0.345 and times it by 100, and you get 34.5. So that is another way to get it. That 34.5. And you can do that for each individual thing there. Like I said, sometimes they're not always going to be exactly 50-50. All right, now 11 of them said no, so if we split that 50-50, that's 5.5 and 5.5. And then the maybes would be 10 and 10. All right, so how far off are we? Well, we do the chi-squared calculation again. We have our expected under the assumption of perfectly equal distribution versus observed. How far off is expected from observed? We go and we do this calculation right here. So you have to start plugging in to this calculation. So it'll look something like this. We have observed minus expected squared. So for the first column, I believe there were 30 men who answered yes when they were asked by a male versus 34.5 that we would expect under a perfect distribution, perfectly equal distribution, divided by expected, and square. And that would be the first one. Then we go to the next one. All right, how about going down the line here? Well, we do that for everything, and we eventually get to the last box, which had 8 female, asked by female and said maybe, and 10 would have been perfect, divided by 10, and there we have it. Now, when you're doing your FRQ for this problem, you have to write this out, write the first term, write the last term. You don't need to do the middle terms, but they do like to see what's called the mechanism. They want to see the mechanism. They want to see that you can plug into the formula, and you can get the rest from your calculator actually, or you can do it all by hand. Doesn't matter. So we could get this from a calculator, or we can do it by hand. 4.25. I'll explain how to do this in your calculator in a little bit. But if you do calculate that out by hand, you get about 4.25. You do for all 6 cells. All 6 cells. All right, now, for two-way tables, degrees of freedom is a little different. You have to know how to calculate this. This is not in your formula packet. Number of rows minus 1 times number of columns minus 1. So for us, find the degrees of freedom, it would just be, let's see here, we have 3 rows, that's this way. We have 3 rows, and we have 2 columns. Remember, columns are like the columns of a building. They go up and down like the columns of a building. We have 2 columns. So our degrees of freedom is 2 times 1, which is 2. All right. Now we have everything we need to run our test and find our p-value. So to find the p-value, you use the table C in your formula packet. You line up degrees of freedom with your chi-squared value, and that will find you the p-value. Or use the chi-squared CDF in your calculator. So let's go into the old calculator and check it out. So in our calculator, this is back to statistics. I'm looking at distributions. This is my chi-squared distribution, chi-squared CDF. Chi-squared CDF looks like this. It's got a big hump and then it tails off. So my lower bound is going to be my degrees of my chi-squared number, 4.25. My upper bound is going to be something ridiculously large, and my degrees of freedom will be 2 in this scenario. All right, that tells us our p-value. So our p-value ended up being 0.119. That's a pretty large p-value. It's not less than 5%. Okay. So calculator p-value, table C, or calculator, and we get 0.119. All right, the conclusion, based off of a standard 5% significance test, we would conclude we would fail to reject the null. The data is not significant, and we would draw a conclusion off of the alternative. We always conclude on the alternative. There is either evidence for the alternative or there's not evidence for the alternative. So in this scenario, we could say, because the p-value is greater than 0.05, we fail to reject the null. There is not convincing evidence of a difference, and now we got to give context, a difference in the response to the question, would you vote for a female president, by those interviewed by a male versus those interviewed by a female. Thank goodness the world is not a terrible place. All right. Although it was close. Yes.
I would like to say something concerning my now sexist reputation.
Oh no. Okay.
This reminds me of.
Yes.
I've learned, and I have witnesses from Liam and Jacob, that Emily fabricated her numbers.
What?
And I deleted all the data off my calculator and got all the numbers, so I could hold that over.
Oh!
I would like to say I'm not sexist.
Oh my goodness.
This is true. Most of those numbers were just
statistics.
They were random. I remember a lot of them. I didn't just make up.
Probably just put them on the calculator and all that.
So fun.
Save their price.
Wow.
I was being attacked for that.
Yeah. Well.
We should redo it.
Yeah, that's interesting. It's very interesting. Huh. We just learned that Ryan is not actually sexist.
We don't know that.
Well, I guess.
There's a possibility he's not.
We're back to not knowing, essentially.
Yeah, wow. But we do know something about Emily now.
This is true.
That's very interesting. Huh. Interesting. Okay, last one. This is called a test for homogeneity. Explain how this test is different from a chi-square test for goodness of fit. Well, a couple things. Goodness of fit only had one sample, first of all, and you're testing it against a claimed distribution. There's still one variable, so it's similar. So for the M&Ms, it was color. It's one variable it's changing. All right, now for a homogeneity test, we're testing two samples and seeing if these samples are the same. Seeing if the distribution of these samples are the same. There's still one variable. Okay. It's the response to the question. Okay, let's see. Is that all I want to say there? All right. The next chi-square test. Let's take our break. We'll cut it there. My coffee. I gotta process what just happened. Fabricated data. Ooh. If you're online, we just learned that Emily fabricated the data of the M&M experiment to frame Ryan as having a gender bias when handing out the M&Ms of the last class. Wow. That's the most drama I think I've ever had in this class. Alright, hold on, I gotta send an email and then we'll get started again.
I'm pretty sure she was. But she really, it's in my group, she just had a name. I can't remember her name, but hold on, so I see her friend's name. Is that her name? I remember. Yeah, no, hold on.
Not to be did something. I like, it's so comfortable.
What's your mind? So, Jake, driving while to school.
Alright, on to the next test. Alright, the last chi-square test, this is for independence. We're going to take one sample with two variables now. So one sample with two variables. So all of these chi-square tests are just a little different. We got the goodness of fit is one sample, one variable. A homogeneity test is two samples and one variable. And now this test is a test for independence. This is a one sample, two variables. So we're going to look at two variables and see if they are, what's the word? The correct word is independent of each other, which means are they related? Does one affect the other? So, you know, I really need to bring my questions into the now, right? We got the whole male-female thing, but we're going to look to see if there is a relationship between the two variables. This is one sample of people between English and math and gender. Okay, so is there an association between gender and preference for English or math class? So interesting. Let's see. In an ideal world, there is no difference. But let's see what these data say. Below is the data for a random sample of senior students. Do we have convincing evidence that gender and favorite class are associated? So you can see it's one sample, two variables. We sampled 114 apparently. We sampled 65 female and 49 male, and these are the results of the preference. And that's just one sample. Describe what it means for two events to be independent. Okay? It means that knowing knowing if an event occurs does not change the probability of another event occurring. One does not affect the other. Okay, so basically in a nutshell, two events are independent if one does not affect the other, knowing one. And we say that probability-wise, formula-wise, is like this. If two events are independent, so going back to probability a little bit here, if two events are independent, then the probability of them both happening would be the same as the probability of A times the probability of B. Versus not independent, so dependent events, the probability of A and B is equal to the probability of A times the probability of B, given A just happened. So that's the difference. All right, this is what that's not what we're doing. We're doing this. We're looking to see, is this the same as this? Opposite would be this and that. So if you remember back to some probability. All right, so here is what we have found. We have found our observed data. And now we have to figure out what would be the perfect distribution of this data if it was perfectly independent. All right, so now comes a little bit of calculation we have to figure out. So we have to do this. If it was perfectly independent, then this would be true. Probability of A times A and B would be equal to the probability of A times the probability of B. All right, so for us, finding this value here, we got to figure out what would go there if perfectly independent. So the probability of being female and picking English would go something like this. The probability of female and picking English would be equal to the probability of female times the probability of English. So for us, that would be equal to, there are 64 out of 114 that picked English. So the probability of picking English was 64 out of 114. Probability, oh, wait, that's right here. 64 out of 114. The probability of being female in this data was 65 out of 114. All right. So the probability of being in this box here would be, did I calculate that? I didn't calculate that yet. Why didn't I calculate that? All right, 65 times 64 divided by 114 divided by 114 ends up being about 32%. So in a perfect independent world where the results do not depend on each other, we would expect 32% of our data to fit into this box. So now multiply that by 114, and you get the number of things that go in that box. So 32% of 114, and end up with 36.4. I'm going to do one decimal place, 36.5. Because, I mean, the more decimal places, the better, but calculation's kind of intense. So one decimal place will do all right. So 36.5. Or there's a shortcut to find these. You take if you look at what we did here, we did 65 times 64 divided by 114 divided by 114 times 114. So actually you cross off one of these 114s, and it turns out to be row times column divided by total. All right, row times column divided by total is what that ends up being. So you could have done 65 times 64 divided by 114. That would have also gotten you 65 times 64 divided by 114. And then basically you're just skipping this step. You're skipping the multiply by 114 step. All right. And that will also get you to the 36.5. So to get the male English count, we would do 49 times 64 divided by 114. So maybe just put that off to the side. 49 times 64 divided by 114. And that would easily find that value right there. That's what's supposed to go there. And that's the same thing for the homogeneity test as well. It divides it up nicely. All right, so that should be 27.5. 27.5. All right, and the next ones, if you do the same thing, so for math, we would do 65 times 50 divided by 114, and you end up with 28.5. And for this one, we should get 21.5. And when we total them up, so doing row times column divided by total, and when you total them up this way, you should get 65. Should get what we got here. All right, so what that means is, this is what we observed. We observed a total of 65 female, and it was distributed 43 to 22. However, under the perfect independent situation, we would have observed 65 and gotten this split. We would have gotten this split. So look, there is a discrepancy between these numbers. But is it a big discrepancy? Is it enough of a discrepancy to say, all right, these two things are not independent? So we'll see. This one should total up to 49. This should total up to 64. This should still total up to 50. And this should total up to 114. But really, we're really interested in this data. We don't need these in our calculations. We're looking at how do these compare to how do these. All right, so we continue. All right, so let's do a proper test. We'll do a quick little write-up here. Do the data provide significant evidence that there is an association between gender and preference of English or math? So we are in a categorical situation. We've got two variables. You could be male, female. You could like English, you could like math. So the first thing you need to do is decide, we're going to do a chi-square test for independence. All right, so first thing we do is we state our hypothesis and our method. Okay. The null hypothesis is the boring one. In this case, there is no association. Or you could say independent. No association would mean they're not related, meaning they would be independent. So you could use the word association, you could use the word independent. Don't use the word correlation. Correlation is a different thing. We haven't learned about correlation yet. It's next chapter, between gender and class preference. The alternative then would be the opposite. There is an association. There is an association. I just do dot, dot, dot. Let's write a little sentence. We will test these by conducting a chi-squared test for independence at the 5% significance level. Okay. Now we're all set. We've stated what we're going to do. We stated the hypotheses. And now we need to conclude the conditions. There are two conditions for a chi-squared test. First condition is the sample has to be a random sample that is representative of the population. I think that is good. So random and representative. I'm going to check it off, but if you were doing this, you would make a nice sentence about it. All right? Don't do it. Don't do this. I'm doing this because I'm going to run out of ink. The second condition is that the expected values all have to be greater than 5. 5 or more. It can be 5 or more. So look at our expected values. We have the lowest is 21.49. So we'd say something like all expected values are 5 or more, with the lowest being, what was that, 21.5. 21.5 for male and math. Okay, we are now set to run our calculation. Calculation, we have to show a mechanism. We have to show mechanism. I'm going to write out this. This is about as little as you need to do. About like that. All right, now I'm going to write the first term. So the first box, which had a observed of 43 and an expected of 36.5 over 36.5. I'm going to do dot, dot, dot. And then I'm going to do the last box. Last box. So that would be 28 and 21.5. Okay. And then probably what I do, now this one's not so bad because there's only 4 terms. There's only 4 boxes. So actually calculating this one by hand really isn't that big of a deal. We could plug that into the calculator pretty quickly. I'm just going to tell you what it is, and then when I'm done, I'm going to erase this and show you how to do it in your calculator, because there's a little bit of a process to get it in your calculator. Our chi-squared value ends up being 6.16. And the question is that a big deal? Is that a big chi-squared value? Well, we got to look at the degrees of freedom. So for us, it was a 2 by 2 table, 2 rows, 2 columns. Our degrees of freedom is 1 times 1. So 1. All right, at this point, we can now find our p-value. We can use table C, or we can use chi-squared PDF in our calculator. But we do end up getting, I'll just explain, I'll just do it for you, 0.013. All right, now that is a, well, you tell me. Liz, what does that tell us, that p-value there?
Plus the significant values.
Yep.
Something that is significant.
Should we reject or fail to reject the null?
What if we rejected them?
We reject the null, and therefore there is sufficient evidence that there is an association. Ah, shoot. A perfect world. There is an association between gender and apparently preference of English or math class. Gosh darn it. All right. So we do have convincing evidence that against the null here. we reject the null and conclude there is an association. That would be my conclusion. Now, to do all this in your calculator, you're going to want to get your calculator out and follow me along here. A little extra step. But that would be a proper write-up on an FRQ. Ooh, I just watched the interesting video, John Oliver, and he mentioned p-hacking. And it's when people pick their data the way they want to pick it so that the p-value turns out the way they want it, kind of like Emily. Like the p-hacking. That's called p. That's actually a thing. Maybe we'll watch that video if we have time. It's really offensive, though, because it's John Oliver. So if you don't like the F word, you should probably not watch it. Just throwing it out there, but that's okay. Anyway, I should record that. Oh yeah, I was going to show you on the calculator. So we have our calculator out, and let me start fresh. All right, so I'm going to go to calculate on my calculator. I'm going to run this. And so what I need to do is I need to plug in my observed values into a matrix. So this is a new thing. We got to go to menu. There is a matrix and vector option when you go to menu. And we will create a matrix. So create a matrix. So one more time. Menu, matrix, create matrix. All right, it says, what do we want? All right, we want 2 by 2. Check. We're just going to plug in our observed values. Very important that you plug in observed. When we plug this into our calculator will do the expected calculations for us. All right, now what we have to do is we have to now save this as a name. All right, so right here in blue, there's a store button. So you got to hit, that's STO. So hit Control, and then it'll put a little arrow there, like that. So it's right there. You can't see it on here, but it's STO. We're going to store it, and I'm going to call it obs for observed. These are my observed values, and press enter. And it is now stored in this matrix. Okay. All right. Now that we have our matrix in our calculator, it's pretty easy. We go to menu, statistics, stat test. All right. For the chi-square, we got the goodness of fit, or we got the two-way. This is a two-way test. Now we have our matrix, so we're going to, it should end up, there it is, observed. We'll hit OK, and I think it actually does it from there. Boom. Just did all the calculations. We got our degrees of freedom. We got our p-value. We got our chi-squared value. And we make our conclusion from there. So, same idea. All right, last page. That is how you do it in your calculator. Now I'd like you to take a minute. You can pair up, I don't care. Read through example 3 and tell me what chi-square test you would use for that situation. Okay. The first one that catches my eye is C, right? C is a one-way table. There's only one variable, and we are comparing. Hopefully, our roulette table is pumping out results that are consistent with what they should be. Otherwise, the roulette table has a bias of some sort. Maybe it wasn't built very well. But what would you say here, Quinn? Oh, not here. Eric, for C, what kind of chi-square test would you use?
Goodness of fit.
That's right. Goodness of fit. How do these numbers compare with what they should be? All right, next. Let's go to the next one. Part A here. Which one is that? We have 2 samples. Shopping in a second. We want to see 2 random samples of shoppers at 2 secondhand stores of the same chain in different cities. So how do these 2 samples compare? What do you think there, Ryan? Yes, homogeneity. That would be 2 samples, 1 variable, comparing if the 2 samples are the same. And then lastly, B is Morgan. Independence. We have 1 sample and we're testing to see if there's an association between degree held and opinion about astrology, apparently. So is there an association there? Here is a chart that kind of sums things up as far as the difference in all of these tests. And there is your homework. And we're done. Ooh, we got enough time. Should we watch that John Oliver on p-hacking?